Rocket Day, and Dr. Damaren is a professor at the University of Toronto in the Institute for Aerospace Studies. And today, to learn about rockets, the campers are making a variety of different types of rockets, including stomp rockets and bottle rockets, which sound like very exciting projects. So I'm sure they have all sorts of questions to help them with these projects. But before we get to their questions, Dr. Damaren, can you tell us a bit more about what you do with rockets at the University of Toronto?
Sure. So good morning, campers. Hope you're having a good day and the camp is going well for you. My area of study is something called spacecraft dynamics and control, which are just a bunch of big words for something very simple. We study the motion of satellites and objects in space, and control is basically trying to make them do what we want them to do. So go in certain orbits and point in certain directions and do things like that. At the moment, we're spending a lot of time on something called solar sailing, which you can imagine having a big sailboat in space. So on Earth, when we go in a sailboat, we use the wind against the sail to move. In space, with a solar sail, we use sunlight pressure, the fact that the sun and its rays exert a pressure on things. And we use that pressure to move satellites from different places, from say close to the Earth, and move them closer to the sun and things like that. So that's one aspect of what we look at as solar sailing. A lot of my job is teaching, so I teach university students about space and spacecraft and satellites, and I supervise graduate students, so master's and PhD students who are studying these kinds of things.
Okay, solar sailing, that's something new that I know I haven't heard of before. That's cool. Let's go to some campers in London. Do you have any questions for Dr. Damaren about maybe solar sailing or something about rockets to help you today? Hi.
How big is a standard size rocket?
How big is a standard size rocket? Well, rockets come in all kinds of sizes. Here at our institute, we launch satellites that have very small rockets, like maybe this big, maybe 5 inches long. And then the biggest rocket that's ever been launched was called the Saturn V. Maybe you've seen that. That's the one that was used to take the astronauts to the moon. And that thing was enormous. It was maybe 50 or 60 meters long, and had enough of a oomph, enough of a push to send the astronauts all the way to the moon. So rockets run all the way from very little to very big, depending on what you want them to do, and ultimately it depends on how big the space vehicle is they're attached to. So hopefully that answers your question. Basically, it's very small, very big, and everything in between. Does that answer your question?
Yeah.
Okay, good.
Oh, thank you. Is there another camper in London with a question? Hi.
Hello.
Is there a special, how do you design the rockets?
How do you design rockets?
Yes.
Well, there's lots of things that go into it. First of all, you need to figure out how much fuel you need. And that depends on the type of rocket. So one of the things you have to decide is how much thrust, how much force you need out of the rocket. And that's going to tell you what type of rocket you should use. If you don't need much force, like just a little bit of a push on a satellite, for example, then we would use just a little chamber with gas in it, cold gas under pressure. We would just open that valve and the gas would escape, and that would put a force on the satellite. So there we would have to decide how much gas to put in. At the other end of the spectrum, for the big rockets, they use typically solid propellants. So this is like a solid fuel, and once you ignite it, it's just going to burn until it's all gone. And you have to decide how much to put in there. So that's the key thing in designing a rocket, is figuring out how much fuel to put in. And that, how much fuel you're ultimately going to need depends on, if you're a rocket engineer, we talk about something called delta V, and that's how much velocity change you need. So if you want to move something that's going 1 kilometer a second and you want to make it go 2 kilometers a second, you're going to need a certain amount of fuel to do that. So when engineers design rockets, that's one of the key things they have to decide is how big and how much fuel is needed. Does that help you out a bit?
Yes.
Okay, good.
All right,
Great.
good question. Thanks. Can we go to another question from a camper in London? We don't have any questions from our other camps on Twitter yet, so London, it's all yours. Hi there.
Hello.
Why does the top part of the rocket uh, uh, separate from the bottom?
That's a really interesting question. Um, when we design rockets, quite often they have multiple, like more than one, what we call stages. So the different parts of the rocket are called stages. And it turns out that rather than have one big rocket carrying all the fuel, it's more efficient. It turns out ultimately it takes less fuel if you break the rocket up into little pieces. So once the first piece is done burning all its fuel, you get rid of it, you jettison it, and then you move on to the next stage, and so on and so forth. So it just turns out that it's actually a better idea to break the rocket up into pieces because ultimately that will use less fuel. But it's a very deep question actually, and it took engineers a while to figure out that that's how you should do it, is by using pieces. So this is why we got to get rid of the first piece and move on to the second piece. And because the first piece is gone, the second piece doesn't have to do so much work, and so on and so forth as you move through the different pieces or stages of the rocket. Does that answer your question?
Yeah.
Great. That's a very good question.
Yeah, thanks. Is there another camper there in London with a question? Hi. Awesome.
Hello.
Hi. How do you eat in space?
How do you eat in space? Well, it turns out that the thing that connects your throat to your stomach, the esophagus, that has very strong muscles in it. And they can even work even if you're upside down. I'm not suggesting you try this, but it is possible to eat even upside down. And that's on Earth. That's with gravity. If there's no gravity, as there is in space, then it really doesn't matter whether you're upside down, sideways, or whatever. The esophagus, the bit that connects your throat to your stomach, it does the same thing regardless. But even on Earth, even with gravity, it is possible to eat upside down. So, yeah. But it's easier in space because you don't have gravity.
Maybe something to try there. Thanks for that question. So we have a question on Twitter now from our camp in Woodstock,
Oh,
sort
great.
of related to the last question. They wanted to know what would happen to regular food in space.
Regular food?
Yeah, what would happen to regular food in space? I guess maybe as opposed to the food they prepare specifically for the astronauts.
Yeah. Well, I guess the trick is to hold it all together. And again, because there's no gravity, I think regular food would break up into many smaller pieces, whereas the specially prepared stuff for astronauts is designed to stay together. It's usually there's liquids involved there to make it mushy, and it's sort of like the difference between mashed potato and a potato that's all cut up. The potato all cut up, the pieces all kind of separate, whereas mashed potatoes will stay lumpy and stay in one piece. So I think that's what would happen.
Yeah. Okay, that sounds like it would get kind of messy.
Yeah. Yeah.
So another question from Woodstock. They want to know, how does fire propel the rocket? So I guess they mean maybe the explosion underneath. How is that fire working?
Okay. Well, it's a very interesting thing. It's based on what we call action and reaction. And there's a very famous guy named Sir Isaac Newton, and you're going to learn about him as you probably when you get into high. Isaac Newton said basically his third law was that if whenever there's an action, there's a reaction. So with a rocket, you've got some fuel, and you ignite it, or you let it go under pressure, and it leaves the rocket. So because it's going in one direction, Newton's law says there has to be a force in the other direction to balance it off. So that's what we call the action force and the reaction force. So when you let fuel under pressure because you've either exploded it or you've had it in a tank under pressure, as it leaves the rocket going, say, down, then there has to be a force in the opposite direction going up. And that's what provides the thrust on a space vehicle. So it's this idea that for every action, there's a reaction. You can sort of get a sense of this when you push against a desk, for example. See, when I push against my desk, I go back in the opposite direction. So I put a force on my desk, so the desk actually puts a force on me in the other direction. And that's this principle of action-reaction. And that's the whole principle underlying how a rocket actually works.
Okay, good question. So I see Ancaster just joined us. Hello, glad you could join us. Are there any campers there with a question about rockets for our guest rocket expert today? I see a hand up.
Okay, so what is rocket fuel made of? You asked that right there.
What is rocket fuel made out of?
What's it made out of? Well, there's lots of different types of fuels. For example, on the space shuttle, those big giant tanks you see there, they use liquid oxygen and liquid hydrogen. And when you bring those together and light it, it gives quite an explosion, like a controlled explosion. In smaller rockets, we use a liquid fuel called hydrazine. It's a very poisonous type of fuel, but it gives a lot of force when you ignite it. Then we have rockets that use more than one fuel. We call those bipropellant rockets, and there we use typically nitrogen tetroxide and monomethyl hydrazine. So those are very fancy names for two chemicals, but the reason they use those is when those two chemicals come into contact, they immediately explode and provide again this controlled expulsion of the propellants once you ignite them. So there's lots of different possibilities. Here at our institute, with our very small satellites, we use a cold gas, and that could be something like nitrogen under pressure. And so as you can see, there's a lot of different possibilities depending on how big the rocket is and how much force you need to get, or thrust you need to get from the rocket. Does that answer your question?
I think so. I see
Okay,
another
good.
hand up. Oh, thumbs
stuff.
up. Good. Is there another question from a camper in Ancaster? Did someone else have a question for Dr. Damaren?
Okay, right into there.
How do rockets work?
How do they work? Well, let's look at a really simple example. So imagine I have a spaceship, and inside it's got a little area like a tank. So just imagine a sphere, like a beach ball, or even, let's think of a simple example. Think of a balloon. And imagine the balloon, we've blown it up and inflated it with gas, and then the part where we were blowing into the balloon, we close that off so that the balloon stays inflated with the air inside it. So there you've got air inside the balloon, and it's under pressure. So it's pushing out against the walls of the balloon. It wants to get out of the balloon, doesn't it, right? So then, when we open up the valve, the opening to the balloon, all that air under pressure is going to want to escape, and it's going to push out of the balloon. And then, based on Newton's third law, this action-reaction principle, because the balloon has put all this force on the air pushing it out, there has to be a force in the opposite direction pushing on the space vehicle. So this is fundamentally how it works. It's based on having propellants, in the case of a balloon, just plain air under pressure. And when that pressure pushes the stuff out of the balloon or the tank or whatever you're carrying the fuel in, you're going to get a force in the opposite direction on the space shuttle or the space vehicle.
Okay. So you keep that in mind as you build your rockets. Pay attention to how the reactions equal opposite reaction. So we have time for a couple more questions. Is there another question in London? I see a hand up. Oh, hi.
Is it true that if there was a rocket with no heat shield, when it entered space, would it burn up because when you enter space, it gets really hot at first?
Yeah, that's right. We were talking about stages earlier, and sometimes we jettison or let go part of the rocket. And if you're up high enough, then you're going faster at that point. So as these jettison pieces, because they're going so fast, they move through the atmosphere. The atmosphere, because you're going so fast, provides a lot of heat, friction basically. Like, it's sort of like when you rub something really, really fast, you start to heat up. Well, basically the atmosphere rubs against the space vehicle, the part that's been jettisoned, and it gets really hot, so hot that it actually melts and that's what we say, it burns up. If you let go of the stuff early, like for example the space shuttle gets rid of its external tanks very early, they're not high up enough, they're not going fast enough to burn up, so they just fall into the ocean without burning up. But if you're up high enough and you're going fast enough, then those things, yes, because of the friction of the atmosphere, will melt and disintegrate into nothing basically. So that's what we mean when we say they burnt up in the atmosphere. Yeah, nice question. Thank you.
Yeah, thanks. Let's go to our final question to a camper in Ancaster. Was there another question for Dr. Damaren there? Excellent.
Hi.
What are the physics behind rockets?
The physics? When we talk about physics, so we're describing kind of how science works. In the case of the rocket, we're studying motion. So the underlying physics, we use mathematics. So in physics, we quite often use math to describe how things behave. And with rockets, we have a very important equation called the rocket equation. All aerospace engineers use this equation when they design a rocket. And basically what it does is it tells you, given the properties of the fuel, or what we call the propellant in the rocket, it tells us how much matter is going to be expelled by the rocket, given the type of fuel, and also what we call the delta V, how much velocity change we want the spaceship to experience. So given those two things, the type of propellant and how much change we want in the speed of the spaceship, that tells us how much fuel we're going to burn. And so that's the key piece of math that we use. It's called the rocket equation.
All right. Well, that's all the time we have for our session with Dr. Damaren. Thank you so much, Dr. Damaren, for calling into STEM Camps today and telling us a bit more.
Great. Well, I hope you all enjoy the rest of your camp. It's been a real pleasure speaking with you.
Yeah, thanks everyone. Thanks for all the great questions.
Bye-bye.